Welcome. In previous screencasts, we learned about the relationship between the degree of the numerator and denominator and the long-range behavior of rational functions. We studied the domain of rational functions, and most recently we learned how the zeros of the numerator and denominator relate to the location of a rational function's zeros, vertical asymptotes, and wholes. In this screencast, we will put all of this together to identify the key features of a rational function. Let r of x equal x squared minus 25 divided by x cubed minus 12x squared plus 35x. Determine each of the following for r of x. Pause the video and try this on your own. Okay, so we know the domain is related to when the denominator equals 0. So I'm going to rewrite this function. We'll go ahead and just factor the numerator and denominator right away. We know we're going to need both of those factors. So we can factor out an x from the denominator, leaving us with x squared minus 12x plus 35. So ultimately we have x plus 5, x minus 5 over the quantity x, and then x minus 7, x minus 5. And so our domain is any value of x that would make the denominator 0, which means we know the domain will be all real numbers except, and we have x equals 0 for that factor x we took out, x equals 7 for the x minus 7, and then x equals 5 from that factor of x minus 5. Next, we're going to look for any wholes in the function r of x. We know wholes appear when there is a common factor. So we see right away there's going to be a whole at x equals 5. And we can look at a table of values to estimate where that whole is. Or we could do a little bit of analysis here and take the limit of the simplified version, x plus 5 over x times x minus 7, as x approaches 5. Remember, this simplified version is not the same because it would not have a whole. But by looking at the simplified version, we can find out the exact location of the whole. We can actually let x equal 5 now and get 5 plus 5 over 5 times 5 minus 7. So we get 10 over negative 10, which equals negative 1. So what we have found analytically is that the whole is at 5, negative 1. And again, we'll check that by looking at a table of values and graph in a minute. Next, we want to identify the zeros of the function. So we know the zeros of the function come from the factors in the numerator that are not in common with those in the denominator. So the 0 is going to come from that factor x plus 5, which means at negative 5 comma 0, the graph will have an x-intercept. The vertical asymptotes happen as a result of the denominator equaling 0, but not the numerator. So we're going to have two vertical asymptotes, one at x equals 0 from the x that we factored out, and another vertical asymptote at x equals 7. And lastly, for the horizontal asymptote, we need to consider the degree of the numerator and the denominator. And we see that the numerator is degree 2 and the denominator is degree 3. So the degree of the numerator is less than the degree of the denominator. And from our previous work, we know that that means the horizontal asymptote is y equals 0. So we've identified all the key features. Let's check them by looking at a graph and a table of values. So on the left, we see the graph of r of x. We notice it has an x-intercept at negative 5, as expected. It has a vertical asymptote at x equals 0 and another at x equals 7. and it has a horizontal asymptote at y equals 0. So the only thing that the graph on the left fails to show is the hole at x equals 5, y equals -1. So the graphing technology will pretty much always miss that hole. But if we zoom in near x equals 5, as we do in this graph on the right, and then trace our mouse on the function until x equals 5, then the hole does appear for us. And we can see in the table that as we let x approach 5 from the left, the output values appear to be getting closer to -1. And as x approaches 5 from the right, the output values are also approaching -1. So this confirms what we did analytically, that the hole for r of x is at 5, -1.